Hello everyone and welcome back to Networks class. Last time in class we discussed the dual of the max flow problem, which turned out to be the minimum cut problem. So we found out that the max flow value is equal to the minimum cut value. And then at the end of class we just started to discuss the Ford-Fulkerson algorithm. So we got as far as describing how the algorithm works, but we didn't see an example of running the algorithm yet. And the plan for today is to first start by going over some of the key concepts present in homework 3.1. And after we're done with that, to go back and do an example of Ford-Fulkerson in the way that that algorithm solves the max flow problem. So let's just jump right into the material by beginning with homework 3.1. So the first part of the homework asked you to discuss the benefits of fine granularity models versus coarse granularity models. And we did some of that discussion in class previously, but I think the key takeaway is that there isn't one model that's the right thing to do in all situations. So what kind of model you do really depends based on the circumstances of the real world problem that you're trying to solve. Then questions 2 through 4 simply ask you to just run a shortest path to kind of see how the drug smuggler escapes out of Arizona. So nothing too complicated over there. In question 4, you had to do some units changing to change the abstract map units ultimately into time units so that we could compute what the delay parameter should be. And then in number 5, when you place a roadblock in a particular place, we saw that the drug smuggler just kind of moves around that roadblock. And this really goes along with the model that we've created for shortest path interdiction. So in the shortest path interdiction, the operator gets to see the attacks and respond to them in a way that he thinks is optimal. And so that's why the drug smuggler just walks around the roadblock that we've placed. So then in section 2, you had to do some more serious computation of various roadblock locations. So for question number 2 in section 2, I asked you what arcs are we not allowing ourselves to put roadblocks on? And it was all of the fake arcs in the model. So all of the arcs that we added simply for the purposes of modeling. So those would be the arcs that go to other US state and to Mexico and then to the escape node. Numbers 3 and 4, you just have to solve for the roadblock locations with various numbers of roadblocks. And with number 5, I asked you what interesting thing happens with his escape plan when we place down 3 roadblocks. So it turns out that when we have 3 roadblocks, he chooses to just run through a roadblock. And that's because the 30-minute delay that he's getting from the roadblock that we've placed is just not big enough of a deterrence. So he's willing to incur that delay because incurring that delay, he still gets a better route than going somewhere else. And that's just because the asset that we're using to interdict his shortest path isn't particularly good. So that's a question for number 5. In number 6, I asked you to plot something called an operator resilience curve. So operator resilience curve is something that's quite useful in analyzing networks in general. So on the bottom, for our particular problem, we have the number of roadblocks. But in general, this would be something like the number of attacks that we have on the network. And the vertical axis here is whatever objective function that we have that evaluates how well the network performs. And the point of an operator resilience curve is that it can really help you figure out how robust a particular network is. So if a particular network's objective is to minimize something, so in our case, Tihomir wanted to find the shortest path out of the state. So maybe the objective is here when we have no attacks. And when we have one attack, it just skyrockets. So that tells us that this network is just not very reliable because we can just go in and break one thing, and all of a sudden, the entire network just doesn't work anymore. On the other extreme is just a network where, regardless of how many attacks, its objective function is relatively flat. So that's kind of a very resilient network, because even if you break down 2 or 3 things simultaneously, the operator always has kind of a fallback plan to go to where he can just walk around the particular places where you've chosen to attack. So there's still always a way for the operator to just recover operation even though there were no attacks. So for the particular problem that we had in the homework, we had an operator resilience curve that looked something like this. So it had a number of little steps to it. And getting an operator resilience curve like this is also quite useful, because suppose that you're trying to discuss the operations of a particular network with somebody, and you're trying to convince them that you really need 6 assets instead of 5 to try to disrupt the operations of this network. Well, the operator resilience curve shows you this. So it shows you that the difference between 5 and 6 is gigantic, whereas maybe the difference between 4 and 5 is very little. So it can tell you things like, well, instead of using 5, I might as well use 3 because I'm getting about the same kind of return. But if I had 5, I'd really start arguing, well, please give me one more, because with just one more, I could do significantly better than with 5. So operator resilience curve are definitely useful things to look at. So the next question was, how does the operator resilience curve behave after 8 roadblocks, and why? And after 8 roadblocks, for our particular example, the operator resilience curve remains flat. And the reason for that is that if you look at the solution with 8 roadblocks, what happens is that the drug smuggler is running a roadblock on every single one of his arcs. And so at this point, even if we increase the number of roadblocks, there is no possible way to actually make this path look worse than it currently is. Which means that the smuggler is just going to stick to picking this path, which is why the operator resilience curve at that point would just flatten out. So another thing to kind of keep in mind for number 8 is that even if you didn't go through the reasoning here, you could always just try it, because you have the code in front of you, and so you could just run it for 9, 10, 11 roadblocks, and you should see this kind of flat curve. And you'll in fact also see that he's not changing his plan at all. He'll sort of stick to the same plan throughout. So number 9 asked you whether our roadblock plans are nested, which means that if I had 2 roadblocks, the optimal location to place 2 roadblocks would just be a subset of the optimal location to put 3 roadblocks. And that's just not the case. So it's not the case that solutions are nested. And the best way to see that is just through the little example that was in the homework. So the example looked something like this. So we had distances of 5 here, distance of 1 here, 3 here, and 0 over there. So if you had 1 roadblock, you would place it on this arc right here. But if you had 2 roadblocks, you would place them in an entirely different location. If you had 2 roadblocks, you would do something like take out these 2 arcs. And so the important lesson to pull out of this is the following: that if I wanted to figure out what's the best location for 2 attacks, it's not the case that I can figure out the best location for 1 attack, fix that, and then figure out what's the next best location to attack. So in this particular example, if we figured out the best location for 1 attack, it would be here. If we fix that and then try to figure out where 1 additional attack would go, it would be something like here. But at this point, we're getting a highly suboptimal solution for 2 attacks, because we're not cutting off the guy from his origin to his destination. Um, and so, really, when you're trying to figure out the best place to attack a network, it's about having a portfolio of attacks that work well together. And so, if somebody tells you that you have 5 attacks, you would go and figure out some kind of combination of 5 that gives you a good result, as opposed to sort of figuring out where the first best one is, then adding another, and then adding another, which would give you a highly suboptimal, possibly result for attacking the network. So that's the basic idea of this nested questions. In number 11, we wanted to increase our roadblocks so that they entirely remove an arc, which meant that we have to set the delay parameter equal to NC, because NC is the computational equivalent of infinity, as we discussed a couple of lectures ago. In number 12, we just had to compute roadblock locations for this other attack value. And then we also wanted to plot the operator resilience curve for that. And what happened was, as we moved from 5 to 6 roadblocks, the operator resilience curve kind of looks like this. So there's a huge jump at 6. And the reason for that is the fact that with 6 roadblocks, we end up entirely blocking off Flagstaff. So if you look at Flagstaff, it ends up having 6 arcs out of it. And with 6 roadblocks, you can just block off all of Flagstaff. And so this jump here is essentially a jump to infinity, because he has to run one of those NC max roadblocks to get out of the state at all. So in number 14, I asked you to plot 2 operator resilience curves on the same plot. So one was for this 30-minute delay, which looked something like this. And the other was for the arc removal. So what happened was we got some agreement, but at this point, arc removal ended up doing a lot better. So this was right around 2 where the split happened, and at 3 we were getting different values for the 2 arcs. So the way to think about this is you can think about this as the 30-minute delay is kind of a weak asset. So this is how well we can attack the network when we have this weak asset. But the arc removal is kind of a strong asset. So this is how well we can do with that strong asset. So the interesting question here is how come the weak and strong assets perform equally well when we have 2 of them? So 2 strong assets end up doing just as well as 2 weak assets. And the reason for this is because this is due to the fact that regardless of which way we attack the network, the drug smuggler falls back to the same contingency plan. So regardless of whether we attack him with 2 weak assets or 2 strong assets, he's going to use the same contingency plan, and it's that contingency plan that actually gives us the value of the resilience curve right here. So how effective our attacks are has absolutely nothing to do with the specific of our attacks. The only thing that it has to do with is what kind of a contingency plan are we forcing the opponent to fall back upon. So that's the key to kind of number 14. And really this kind of analysis of comparing 2 different kinds of assets is a very useful one to do in network analyses in general. So that brings us to the last section of the homework, which was just some questions about solver options. So the main thing to pull out of here is the following. So GAMS itself is not a solver at all. So GAMS is a modeling language. And what happens is you write your GAMS program, and from your GAMS program, GAMS creates a problem that then it sends into Cplex, which actually does the solving, and then Cplex sends an answer back to GAMS. And so at the beginning of the GAMS programs where we could choose Cplex or Coin CBC, what's happening is we're actually switching out the solver that GAMS uses. So we could tell GAMS either use Cplex or use Coin. and then GAMS will use that solver to actually get us an answer. But the point is that these software programs down here, they have a lot of kind of knobs you can touch that tell the solver how exactly to go about solving your problem. And so in this section, you got just a small introduction to that. So the first kind of introduction that you got was to something called EPInt, which is a solver option for Cplex, which tells Cplex how close to an integer solution a number has to be for that number to be considered an integer. So in particular, imagine that you're solving the LP relaxation for a network interdiction problem. And here you have an x variable. And in the LP relaxation, it has to be between 0 and 1. So if EPInt is something small, it means that this x variable has to be really close to 0 or really close to 1 for it to be considered an integer. But if we set EPInt to something big like 0.5, then if you're on this side of 0.5, you're going to be considered 0. And if you're on this side of 0.5, you're going to be considered 1. And so that's why when you set EPInt to be equal to 0.5, what happens is even though we're asking for 4 roadblocks, you end up getting 5 roadblocks out. And the reason that we get 5 roadblocks is because our GAMS loop looks something like this. So we loop over arcs ij, and we filter these arcs by the x values that are bigger than 0. And then here we do our printing. And so as long as this x value is bigger than 0, a roadblock location is going to get printed out in our output file. But if you actually go and look at the x values for those 5 arcs, what you'll find out is that some of them are set to 0.3 and some of them are 0.7. And GAMS thinks that those are integers because, or Cplex thinks those are integers because we specified EPInt that way. And so it's going to call that an optimal solution, even though we're not getting integers the way that we wanted for our various roadblock variables. So that's the basic idea behind EPInt. So EPGAP is something that specifies how close to an optimal solution you have to get. And it's kind of a relative specification. So in particular, it would be something like upper bound minus lower bound over the upper bound, which means that EPGAP is a number between 0 and 1. And so if we set EPGAP to 1, that means that this upper and lower bound can be very far away from each other. And Cplex will say that it arrived at an optimal solution. But if you set the EPGAP to 0, then the upper and lower bound essentially have to be equal to each other before Cplex thinks that it has an optimal solution. So the reason that this exists is because in real life, you often end up writing some mixed integer programs that are just way too difficult to solve. And so we don't care about solving them to optimality. Maybe we only care about solving them to within 5% of optimal because 5% is good enough for the particular operation that we're doing. And so EPGAP lets you tell Cplex that fact, that you're willing to just tolerate something that's within 5% of optimal. And by the way, if you actually knew the units of your objective function, if your objective function was measured in fuel or something like that, gallons of fuel, then you can specify an absolute tolerance here. So you could say, I'm willing to accept the solution as long as I'm within 5 gallons of fuel or 10 gallons of fuel. But that is based on the units of your problem, while EPGAP here is just independent of units because it's a ratio about how close in terms of percentage you are to an optimal solution. So that's the basic idea behind this parameter. And of course, if you set EPGAP to 1, you end up getting a solution that's not optimal. So we end up getting a solution that places the right number of roadblock locations, but it leaves an escape path that's actually better than the one that we got earlier in the homework assignment. So that means that our roadblock locations are not optimal. In the last part of this section, I asked you to play with a couple of other knobs, which are start alg and subalg. So those are the algorithms that Cplex uses during branch and bound. So in general, when you give Cplex a linear program, what it does is it looks at the structure of your linear program and tries to guess at the fastest LP algorithm that it has to try to solve the linear program you gave it. So oftentimes, so in particular, if you pass it a network problem, what it'll do is it'll go and look at the columns to try to see, does each column have exactly 1 plus 1 and minus 1? And if it does, it's going to know to use an algorithm that's special to network problems. But oftentimes, Cplex might guess incorrectly. So maybe it uses a barrier algorithm or the simplex algorithm when it was intended to use, or you intended it to use, the network simplex algorithm. And so that's what these two knobs right here let you do. They let you specify to Cplex exactly what algorithm to use for solving your linear programs. And for our particular example, the reduction that you got was not very big. So barrier, for me, gave a running time of 0.08, and network simplex gave a running time of 0.00. So still a lot faster, but even barrier was doing pretty well for the small problem that we were asking to solve. By the way, network simplex is a very general purpose network solving algorithm. So it's much more general than Dijkstra's or Ford-Fulkerson or something like that. But it's also a little bit slower than those. And so if we have time at the end of class, I'll just do a brief overview of network simplex and how it works. So that concludes our discussion of homework 3.1. So let's move on to the second part of class today, which is just looking at an example for running Ford-Fulkerson. So let's begin with just a graph that has a number of edges with capacities on it. So let's say S, 0, 1, 2, 3, and T. And let's say that the edges we have here are an edge of capacity 16, capacity 13, 4 up, and 10 down, 12 in this direction, 14 for this edge, 4, 20, 7, and we'll have one diagonal edge here that has a capacity of 9. So this is the network that we're given, and we'd like to move as much material from S to T as possible. And we're going to use Ford-Fulkerson, which repeatedly finds paths between S and T, and then adds as much material on those paths as possible. So here's maybe the first path that we identify. So let's say that it's S, 0, 2, 1, 3, T. So let's make sure that that's a path. So that's S, 0, 2, 1, 3, T. Yep, that's a path. It's a perfectly fine path. And so let's figure out how much material we can move on that path. And that's determined by the minimum amount of capacity on all of these edges. So minimum of 16 and 12 is 12. Now it's 9, and now it's 4. So the minimum here is just going to be 4. And so after we add 4 units of flow on this path, we're going to get a new graph, because now we have to think about paths in the residual graph as opposed to the original. So let's see how this residual graph works. So to do the residual graph, the easiest thing to do is to first copy all of the edges that we didn't touch on our path. So for example, this edge from 3 to 2, we didn't touch it, so it's going to stay there as 7. This edge from 2 to T, we didn't touch it, so it's going to stay there as 20. This edge from S to 1, we didn't touch that one, so it's going to stay there as 13. And then this edge from 0 to 2, we didn't touch that either, so it's going to stay there as 12. But the other edges, we did touch the edge from 0 to 2. We touched it right there. So we're going to leave that one out. But we didn't touch these edges from 1 to 0. So there, we're going to have a 4 going up and a 10 coming down because we didn't touch that. But the rest of these edges we did touch. And so let's now figure out what the residual is. So from S to 0, we used to have a capacity of 16, but now we're sending 4 in that direction. So the remaining capacity we have there is 12. In the reverse direction, we have a residual capacity of 4 that corresponds to backing up on the 4 trucks that we're sending from S to 0. So a similar thing between 0 and 2. So the capacity in this direction is going to be 8, and in this direction is going to be 4. From 2 to 1, the capacity in this direction is going to be 5. So that used to be now 9, and it decreased by 4, so it's 5 now. And in the opposite direction, it's going to be 4. From 1 to 2, in this direction, it's going to be 10. And in the opposite direction, it's going to be 4. And from 3 to t, the original capacity was 4. We're sending 4 trucks, so no more capacity from 3 to t. So we're not going to draw that edge in because it has 0 capacity. But from t to 3, we have a capacity of 4 because that corresponds to backing off on the 4 trucks that we're sending. So that's now our residual network. And so now when we find a path from S to t, we have to do it in this residual network. So let's say that the path that we found is the following. So let's say it's S0, 1, 3, 2, t. So let's make sure that this is a path. So S0, 1, 3, 2, t. Yep, that's a path. So how much material can we put on that path? So this has a capacity of 12. Now the minimum is 10. The minimum is still 10. Now it's 7. So we can put 7 trucks on that path. So let's see what the residual network looks like after we put those 7 trucks. So again, the easiest thing is to first copy down all of the edges that we didn't touch. So we didn't touch this edge from S to 1. So that's going to remain as 13. We didn't touch this edge from t to 3. So that's going to remain as 4. We didn't touch these edges between 0 and 2. So this is going to remain as 8. And this is going to remain as 4. We also didn't touch these diagonal edges, so those stay. So this is a 5 and a 4. But the rest of the edges we did touch, so let's fix those. So we had a capacity of 12 here. Now we put 7 more trucks. So what we have left is 5. In the opposite direction, we used to have 4. But now we increase the flow in the opposite direction by 7. So we're going to have 11 on the way back. Down here, we used to have a capacity of 10. But now we increased it to 7 trucks. So the remaining capacity here is 3. And in the up direction, we used to have a capacity of 4. But now this number is 11 because we increased the flow in the opposite direction. From 1 to 3, in this direction, we're going to have a 3. And in the opposite direction, we're going to have 11. From 3 to 2, we have a 0 because we used to have 7, but we maxed all of that out. So no more capacity left in the vertical direction. But going down, we have a residual capacity of 7. From 2 to t, it used to be 20. Now it's 13. And 7 back. Okay, so that's our second iteration of Ford-Fulkerson. In our third iteration, we're going to find a path in this residual network. So let's say that the path we find is S 1, 2t. So let's make sure that this is a path, S1, 0, 2t. Yep, that's a path. And how many trucks can we put on that path? Well, right now 13, now it's 11, now it's 8, so 8. So we're going to once again draw a residual network for this. So our path went like this. So I didn't touch this 4 edge. I didn't touch this 7 edge. I didn't touch this 3 and 11. And we didn't touch these diagonals either. So the 5 and 4 stay. And I didn't touch these from S to 0 either, so that's going to give me this 11. And the 5 going in the opposite direction. Okay, so then from S to 1, we used to have a capacity of 13, but now we put 8 trucks. So what's left is 5. And we have a reverse arc with a 8 on it. That corresponds to backing off on those 8 trucks. So let's see about this vertical arc. So we used to have a capacity of 11, but now we used up 8 of that. So what happens is we have 3 left vertically and 11 going down. On this arc from 0 to 2, we used to have a capacity of 8, and we've put 8 trucks there. So this capacity ends up getting changed to 0, and the reverse capacity gets changed to 11. Or rather to 12, because that's 4 plus 8, so 12. And from 2 to t, we used to have a capacity of 13. We put 8 on there, and so we're going to have 5 left and 15 going back. So let's do one final iteration here. So we need to find a path in this residual graph. So let's say that the path we find is S1 to t. So S1 to t, yep, that's a path. So what's the delta on this path? Well, 5, 4, so it's got to be 4. And now we can draw our final residual network. So didn't touch this edge, so the 5 and 11 just stay here. We didn't touch this edge, so this 12 remains. Didn't touch this edge, so this 4 remains. Didn't touch this one, so the 7 remains. The 3 and the 11 remain, and then this 3 and this 11 remain. But the rest of the edges we touched. So let's think about what happens from S to 1. So we used to have a capacity of 5. We put 4 trucks on there, so only 1 capacity left. And on the way back, we have a 12. From 1 to 2, we used to have a capacity of 4. And we used all of that capacity, so that means nothing left over there. And in the opposite direction, we have 9. And then from 2 to t, we used to have 5. We used up 4 of that, so we have 1 left. Which means that from t to 2, we have 19 left. So in the next iteration of Ford-Fulkerson, we'll try to find a path from S to t, but there is no such path. And that's because we're encountering all of these edges that are pointing back in the opposite direction. So there's no way for S to reach t right now. And so this is the final residual graph. And we know that it's the final one because there was no path from S to T. So it turns out that the keys for this problem are this final residual graph and this original graph. If somebody gives you these two graphs, the original graph and the final residual, then that's enough information to pull out the entire trucking plan, to figure out what the max flow is, to figure out when the min cut is, etc. But let's see why that is in a few small steps. So first, let's figure out what was the maximum flow. So what is the max flow from S to T in this example? So one way we can answer this is to just add up all of the deltas from the various steps that we did. So let's do that. So we have 4 plus 7 plus 8 plus 4. So 4 plus 7 plus 8 plus 4, which gives us 23. So that's one way to figure out what the flow was, is just add the deltas. But there's another way, which is that we can just look at the total amount of material that's leaving S and the total amount of material that's entering T. So let's do that. But first, let me copy some of this material over to another page. Okay, so somebody gives us the original graph, the final residual graph, and they want us to know what's the max flow from S to T in this example. So at this point, we no longer have access to the deltas. So the only way to figure this out is to try to back out what the trucking plan is from taking a look at these two graphs. So one way to figure out what's the flow from S to T is to just look at what's the total amount of material that's leaving S. So to do that, we have to figure out how much material is flowing on this top arc from S to 0. And you can do that by taking a look at these two graphs. So originally, we had a capacity of 16 going from S to 0. And now we have a capacity only of 5 left. So that means that we had 11 units flowing from S to 0 in this top arc. Similarly, how many units did we have flowing from S to 1? Well, the original capacity was 13. We now have a capacity of 1 left, which tells us that there must have been 12 units flowing on this bottom arc, which gives us 23 units leaving S. So as expected, that adds up to the sum of all the deltas for the various iterations of Ford-Fulkerson. So the key thing to pull out here is that when we compare these two graphs, we can tell exactly how many trucks are flowing on each edge. So for example, let's take a look at this edge from 2 to T. Its capacity used to be 20. It now went down to 1. So that means there must have been 19 trucks going across that edge. But let's take a look at a more complicated example. Maybe this stuff between 0 and 1. So now we had edges in both directions. So there were edges in both directions in the original and edges in both directions in the final residual. So how do we know which way the trucks are flowing and how many trucks? The basic idea is the following. So number one, just look at the direction where capacity decreased. The trucks are flowing in that direction. Only in that direction. So let's take a look at these two edges that we had as an example up here. So in which direction are the trucks flowing? So if I look at this 10, it was pointing down, and in the final residual, the 10 got increased to an 11. And so the trucks are not flowing in this direction. But if you look at the other direction, its original capacity was 4, and now it got decreased to 3. So that means the trucks are flowing from 1 to 0. And the number of trucks is equal to the magnitude of the decrease. So that's how we knew that there was one truck flowing from 1 to 0. So let's apply that same rule to a few other places. How many trucks are flowing from 1 to 3? Well, the original capacity was 14. In the residual, that got decreased to 3. So that means there must have been 11 trucks flowing from 1 to 3. How many trucks are flowing from 0 to 2? Well, the original capacity was 12. It got reduced to 0 because this arc wasn't even here in the final residual. So that means that 12 trucks were flowing from 0 to 2. What about this edge from 2 to 1? How many trucks are flowing from 2 to 1? Well, the original capacity is 9. In the final residual, the capacity is still 9, which means 0 trucks are flowing from 2 to 1. So let's do the same exercise to compute the total number of trucks entering T. So in this top edge, the capacity was 20 originally. Now it's 1, which means that we had 19 trucks coming in on the top edge. On the bottom edge, the original capacity was 4. At the end here, it's 0. So there were 4 trucks on the bottom edge, which is 23 trucks entering T. And of course, not surprisingly, this 23 matches up for leaving S, entering T, and adding up all the deltas. So let me ask another question. So from S, we cannot reach T. That's what gave us the final residual. But the nodes that S can reach define an ST cut. So in particular, what are all of the nodes that S can reach in the final residual? So here, I mean in the final residual. So what are all the nodes that S can reach in the final residual? Well, in this particular example, S can reach S, it can reach 0, it can reach 1, and it can reach 3. But it cannot reach 2 or T because of all of these edges pointing in the opposite direction. So 2 and T are over on the other side. So this is an ST cut because this is S's side, and this is T's side of the cut. So let me just draw it in here. It kind of looks like that. So it divides the graph into S's side and T's side. The natural question to ask is, what is the residual capacity of the ST cut we defined? So we define this ST cut by looking at all the nodes that are reachable from S in the final residual. And its residual capacity is just the sum of all the arcs that start at S's side and end in T's side in this residual graph. So there are no arcs that start in S's side and end in T's side. And so the residual capacity of this ST cut is 0. And this should be completely not surprising because that's how we define this cut. If there was some arc going from S's side to T's side, that means that there should have been another node that's reachable from S. So it's always the case that the residual capacity here is 0. Another way you can think about this is that this is the place which is stopping me from moving more trucks from S to T. Because I have no more capacity, no more residual capacity to move material across this cut. So this ST cut is the bottleneck in the network. So that is really what's stopping us from moving more material from S to T. So in particular, it's the minimum cut is defined by this division from S side to T side. So what is the capacity of the ST cut? We defined? Well, its capacity, since it's the minimum cut, had better be equal to the maximum flow value, because we know that the capacity of the minimum cut has to be equal to the maximum flow value because these two problems are duals of each other. So let's check if that's true. So this is the cut in the original network. And the capacity of the cut is just the sum of the capacities of the edges that start in S's side and goes to T's side. So that would be 12 for this edge right here, plus 7 for this edge right here, plus 4 for this edge from 3 to T, which gives us a total of 23. So we should be very happy about that because the capacity of the minimum cut is exactly equal to the maximum flow value. And so why didn't we include this edge from 2 to 1? Well, because it's pointing in the opposite direction. So it's going from T's side to S's side. And so it's not really part of the bottleneck. In fact, if you look at this edge, we're not sending any trucks on that edge if you compare the original and the final residual. But it's really these three edges from 0 to 2, from 3 to 2, and from 3 to T that are stopping us from moving more material from S to T. So just as a few final comments about Ford-Fulkerson is you can think of Ford-Fulkerson as kind of a little special LP solver. So by having these two answers, or these two graphs, the original and the final residual, we can pull out all of the variables for the max flow LP and for the minimum cut LP for an optimal solution. So in particular, we know what the value of the V variable is. So V was just the total amount of material we're moving from S to T. We know that that's 23 just by looking at these graphs. We know the value of each of the Y variables. So the Y variables specified how many trucks were moving across each of these edges. So we had a Y13, and by just looking at these two, we know that Y13 is equal to 11, because that's how many trucks are moving from node 1 to node 3. So that gives us a way of specifying all of the primal variables. And similarly, we can specify all of the dual variables. So the dual row values just told us which side of the minimum cut a node was on. So for all of these nodes over here, they would have a row value of 1 because they're on S's side. And all of these nodes over here, they would have a row value of 0 because they're on T's side. The dual problem also had some pi values. And so the pi values are just going to be 1 for edges in the minimum cut. So what are these edges that are in the minimum cut? Well, it's exactly these three edges that are the bottleneck. It's the one from 0 to 2, the one from 3 to 2, and the one from 3 to T. So it's just for those edges that pi is going to be equal to 1. And for all the other edges, the pi's are going to be equal to 0. So really, Ford-Fulkerson is a little special purpose LP solver. And the same is true of Dijkstra's algorithm. That's also a little special purpose LP solver where you can just, at the end of Dijkstra's, kind of backtrack what all the values of the primal and the dual for the shortest path problem need to be. So that concludes our example for Ford-Fulkerson and lecture for today. Thanks a lot for listening, and I'll see you all next time.